Okay, I'm the Geoff Nugent part of the show, and this is Fritz. I'm a inspector of mines from Mackay in Queensland, mining inspector, coal. We regulate both underground and open cut, and Fritz is a inspector of mines, occupational hygiene. And we're just going to talk today about a journey we've had over the past few years with our experiences with polymerics, and also some of the research and findings we've got. I presume, with this audience, that there is a bit of familiarity with polymerics, a two-part product that's used in underground coal mining for ground consolidation, and obviously these products are used in metals mines, tunnelling and so forth. So they're a fairly common product, been around a long time, but I'm going to talk specifically, or we're going to talk specifically today about underground mining and the coal mining, and the two key areas that they're applied on the longwall face is void fill to fill cavities, and injectables on your right hand side for securing the structured zones and mining through them safely. So they do use the products for other things underground, such as maybe injecting into ribs to eliminate oxygen out of the GOF. We're starting to see new products come online with liners and that sort of thing. But this is the main area that we're going to talk about today. And with that, there's two key hazards. The first one is biological, okay? And personal exposure with isocyanates, and that's what Fritz is going to talk about a bit later. There's been a lot of testing done there. And the second one is exothermic. That picture you see there, that's some of you might recognise it. I won't play the video. That's Pike River Mine, where they had in the tunnel mouth there was a sea container preparing for re-entry, and they used polyurethane resin to gap the void. Much against, I was actually there for that, with Queensland Mines Rescue at the time. There was advice not to do that, and you should have a look at that video, and in real time it will show you how polyurethane, its exothermic reaction, misused, can get away from you really quickly, okay? And that was probably a dozen years ago. There's also, obviously, incidents up in Queensland that polyurethane resins have been attributed to, the Grosvenor explosion. Whether you accept that or not, it's a finding from the Board of Inquiry and also from the regulator's investigation. And there have been more recent incidents actually. The US in the last 2 years has been fires underground in coal mines using these products, or misusing, and also in Western Australia in the hard rock mines. So the way we've regulated over time in Queensland, prior to 2018, basically we just run off the back of the New South Wales licensing system, okay? The experts would come in, the mine would engage the contractor, and they would go and apply their system in the underground mines. 2018, obviously we worked out it's used fairly extensively in a lot of mines in Queensland. 2018, a recognised standard was developed. So we've got recognised standard 16, which covers off on the controls for biological. It still refers to the German permit and to the licensing process in New South Wales that these people have to have. So what was their need for change? So a number of things have happened. So a lot of these products were developed in Germany, Poland, those sorts of places, and their testing facilities no longer exist. And obviously it's not the same products from 20, 30 years ago. There's new products coming on board. And the other thing with these new products, like spray-on liners, right? So they weren't catered for in our standard. Again, with exclusion zones, where do they come from? Why are they there? What's the science behind it? And obviously, we rely heavily on the regulator down here with the licensing system, and it's probably an appropriate time for us to review and stand on our own 2 feet, I suppose, and sort of control the risk with us and our general managers and SSCs to own the risk. And then, of course, what happened? Grosvenor mine blew up amongst all that. So, as I said, whether you agree or not, one of the findings was that PUR, which was injected in the face a number of days before the explosion, and I actually was on that, well, went down on that face and had a look. They actually injected about, they had 38 holes into the canopy, into coal. Every hole went to maximum volume. So the maximum volumes for ejection in an underground coal mine for PUR is about 200 kilo, or 180 litres, okay? And normally you would see, as you pump, pressure build up, but that wasn't the case. And that product and that coal found itself in the Geoff pretty much right behind the shields for a period of time before the explosion. And the other thing, we want to understand inhalation risk a bit more. So the Board of Inquiry, plenty of recommendations, but that's one of them. The industry undertake research into polyurethane resins to determine the extent to which their use poses a risk of initiating spontaneous combustion. So there's two parts to it. Obviously it's the polymeric itself, but when you have a disproportionate accumulation mixed with coal, what does it do to the temperature of coal, advancing the spontaneous combustion process? And as the coal people will know, you know, you might have a piece of coal in an underground coal mine that's, say, in a seam of 35 degrees. That'll take a journey, the oxidation process, and when it gets to about 80, 90, 100 degrees, it starts to hit that crossover and then it becomes exponential. So what does this product do to augment that? And that's also what we wanted to look at. So off we went and did some research, and we wanted to find all the objective evidence that supports the controls, like the 350 metres, like the firewatch, like the injection volumes. And what we found was this: duck eggs. Everyone had an opinion, but there was no tangible research that we could put our hand on from anywhere. And we've been using these products in Australia for decades, okay, particularly in underground coal mines. So what we did, and what we've been doing the last few years, is that we've engaged all the suppliers, operators, and we're running a workshop process for these people to assist up, because everyone has a vested interest, because it is a good product. It's not something you want to take out of the mines. It makes mines safer, used correctly, particularly in, you know, in very difficult geotechnical conditions. So all these people have been along on the journey, and we've also involved the New South Wales regulator. We've kept these guys up to speed and invited them in on our meetings, and they've been excellent. So we're just about at the back end of the whole journey. And we're going to share some stuff with you. So I'm just going to talk about exothermic, okay? So what we wanted to do was understand the behaviour of the product mixed with coal. So we did two things. One was we used the exothermic, trying to think of the name of it, forgot it.
Thermostats?
Thermostats. When we were ejecting into coal, mines would do these trials for us, and we also did testing at SIMTAS. We did large-scale testing, and what we wanted to understand through the laboratory testing was the impacts of the exothermic reaction, determine the parameters of the temperature monitoring, like what we need to monitor, how long for, what's it look like, and determine the time for coal to be impacted and come back to normal temperature. So I'm just going to talk about the testing we did at SIMTAS. So what we did, and this is all, you know, the suppliers were all part of this process as well. We did the risk management and the design of the methodology. So what you see there are 600 mil square culverts, concrete culverts, and they were designed. And we had a headspace on the top for gas, and we had 4 thermostats in there: lower, middle, top. Okay, and you'll see to the left that was where the product was injected. These suppliers, who are all de-identified by the way, came and injected the products themselves professionally. Right, then what we did. So we had 3 scenarios. You'll see those pits. We had pure mixed product, so that was just, and what I'll talk about here, that the size of those pits are about the volume of a hole. So what we wanted to see, if you lost control, if that product never injected into the cracks and fissures and that product disproportionately accumulated, what's that look like, you know, in that sort of volume? So it was more realistic. Then we had run a mine coal. So we had 12 tonne of coal, green yellow middle seam coal, sent down to us kindly by Anglo, in those big 1 tonne bottle things. Anyway, so we had run of mine coal and we had run of mine wet coal. So we put moisture in the coal, okay? And the moisture was, tested each day and measured. And there were 3 pits for redundancy, okay? So the products we tested were standard PUR. So your standard PUR, the temperatures are normally up to about the 146 degrees mark, okay? There's a bit of an arms race going on with the product suppliers to get these low reaction PURs. And those PURs are running around about, 90 to 100 degrees. Urosilicate, again, 2-part product, performance a little bit different. It gets up around the 100 degree mark, and there was an acrylic resin that another supplier wanted to trial as well. So I'm going to get straight into the results. So what I'm going to show you here is just a snapshot of some of the findings. This was done over a couple of months. A trial took about 3 to 4 days. And we had Simtaz had all the computers and monitoring and systems set up. There is a full report. It's completed. It's not published yet. Probably will be published in the next 2 weeks. And there's a lot more data and information on decay times and so on. So we'll have to take this in context. So maximum temperature. So at the moment, the current method of testing polymerics for approval for temperature is in a cup, 250 mil, right? Mix the product, put your thermometer in, read what the temperature is, pass fail, right? So we looked at obviously larger volumes, and if you have a look at on your right hand side is the cup test temperature, and this is the standard, this is the product temperature mixed on its own, not with coal. So you can see a bit of an appreciable difference in temperature. So it kind of makes sense, I suppose. If you get a bit more product and it's confined and it's insulated, you're probably going to see a bit more temperature increase. These temperatures no products exceeded 150 degrees, which is the legal requirement for Queensland and New South Wales. Okay, next slide. How long did it take to reach that temperature? So again, you look to the right for all these products, you've got your cup test. 10 minutes, 11 minutes, and then we found a couple of products were like 12 hours, 11 hours to reach it. So it got to its peak or near its peak and just maintained it for 12 hours. So, and this is kind of the theme that's coming out. Not all products are created equally. They might be called a polyurethane resin, they might be called, the chemistry may be similar, but you need to understand your product and what its behaviours are. So, next one, longest time to reach back to injection temperature. So, all the products were put in a cold room at 25 degrees and brought out, and most of the testing was done sort of September, October time up in Redbank, Ipswich, Queensland. So what we found, now this is probably a little bit misleading in some ways, and we wanted to see how long it come right back to that start temperature. Now the decay curve, which you'll see in the report, does come off pretty rapidly, but it hits, a lot of these products hit a particular point like say 70 degrees, 60 degrees, and there's a very long tail. And that's an important bit of information to understand because that's what's sitting, if you lose control of this stuff, that is what's sitting in your GOF or in your cavities or whatever it might be. So the longest one we had 153 hours and 126 hours, so it was quite a long tail. And that sort of goes to, well, what's that mean for the firewatch? Okay, if you lose control. Now I'm on to the run-of-mine coal and the wet coal, okay? So, and these maximum temperatures, okay, these maximum temperatures are from one probe. It's the highest probe. So, again, if you look across, obviously if you mix it with coal, you're going to have that heat transfer. You're not going to get that maximum 146, but they're the sort of temperatures we experience, 127 degrees in standard coal, and 126 degrees in wet coal. So just an interesting point, some products, when you get moisture, they will increase in temperature. So that's something else that we're going to have to consider, the behaviour of the product, where you're injecting it, do you have a lot of water and what happens? And that was another one as well in blue, where you had an increase in temperature with the wet run-of-mine coal. So this one, longest time to reach maximum temperature from injection. Okay, so you'll see that in the coal, if it's controlled in the coal, the time it takes to get the maximum temperature isn't that long. And the other thing we found, you always learn stuff when you're doing this sort of research. Some of the mixtures weren't uniform throughout the coal. We could probably do the process a little bit differently and better to get a more uniform mix, but it's what we had. So, longest time to reach maximum temperature. So we actually found that some products will take longer to reach maximum temperature in the wet coal. Right. Longest time to reach back to injection temperature. This is with the coal. This is the stuff about the Firewatch, okay? So how long did it take? So some of these products were up to 60 hours, okay? Interestingly, with the wet coal, the time to come back to original temperature was shortened significantly. So a lot of this data was surprising to us, okay, and I'm sure it's surprising to you, some of you, in the underground coal sector. And what does it mean? And as I said, this data the report has a lot more, the decay curves, which gives more, I suppose, perspective with the numbers. But I suppose the other thing is, when up in Queensland, what we're looking at is the testing for mines to bring on site. If it's a particular product, okay, that reaches or exceeds a certain temperature, do we need to do more testing rather than a cup test? So that's the type of stuff we're looking at the moment. And what we're also looking at is definitely putting a lot more, well, they own the risk anyway, the operator in the SSE. So the recognised standard is certainly going to put a lot more onus back onto the operator in the SSE to own and develop the system, but also have this information for their risk management. Okay, so this is the critical stuff, the technical stuff you've got to have for your risk management and understand what's appropriate. So just some key takeaways from this side of it, right? So as I said, PURs and these products used correctly are excellent. And also what we found underground, I don't have the data up here, but when injected into the correct environment underground, we got really good results. But an important thing you want to think about is proactive injection. On a longwall face, you know where the faults are. Why don't we inject in advance of the face rather than waiting until it falls in and react? Certainly that's going to happen at times. So and there's a lot more of that going on in Queensland, proactive injection along the fault lines in the tailgate and the main gate. Okay, correlating your field results and your laboratory results and developing your own design criteria. So not all products are equal, so not all products are suitable for particular applications, particularly in a face situation where it's going to report to the GOF. There's probably safer products to use. They may not have the ideal performance that you want, but they're the most appropriate product. Things like, triggers for injection pressures, right? I can tell you for a fact at Grosvenor, and this happens at many mines, you start pumping, right, and you don't get any back pressure on your pump or on your gauge, well, where's it going? You should be getting back pressure at some point, so there should be triggers for that. Temperature monitoring. I think now up in Queensland, there's a lot of the operators are taking it on themselves because they've been part of this trial. They're actually using thermocouples to test and monitor to see what the behaviour is like between the holes and that sort of thing. So that's a few of the takeaways. This is what so we're using a novel approach, a thing called risk management, so to develop this recognised standard. So we're using this report and the other data we got from the mines to inform the recognised standard with the subcommittee. So that's just a bit of a snapshot. You'll get a report, there'll be a report out. This is sort of what we're going to base our standard on. And I'll hand over to Fritz to talk about the biological stuff.
Thanks, Geoff. Yeah, just before I start, I'd just like to emphasise one of the points Geoff touched on earlier, and that while this is very much focused on coal, just remind you that back in 1986, one of the largest mining disasters of the modern era was at Kinross mine. 177 people died that day, and that was when polyurethane foam caught fire in the mine. Another 250 were severely incapacitated as a result of that fire. And dealing with the supply as closely as we have been, we're seeing the footprint of these products head more and more into the metalliferous mines. And from my perspective, one of the good things about the licensing system that we have down here in New South Wales, we've adopted there, it places a lot of onus on the approval process of the products, but also in the conditions in which they're used. And that does not exist in the construction industry, in the tunnelling industry, and at this point of time in the metal mines. And that's something as regulators and an industry we need to be on the front foot about. Thanks, Geoff. Now, my talk is focused on the personal exposure side of things, and specifically on the exclusion zones that are in force here in New South Wales and in Queensland to prevent that exposure. And in the case of polyurethane resins and urea silica resins, what we're trying to prevent is inhalation of isocyanates. If you know anything about isocyanates, they're found in other products such as spray paint, but they are very powerful respiratory irritants and sensitising agents. And the exclusion zone we have in place for when we pump, inject, spray isocyanates or polyurethanes underground is 350 metres. Now that is an excessive distance, but we have a really serious hazard that we need to control. But is it the right number? What we wanted to understand is what is the actual inhalation risk when using these products. And when we dig deep into this, we try to understand where did the number come from. Now, over the last 20 or so years, working in and around the industry, dealing with these products, I've asked many questions about this, and I've had about 6 different versions of the origins or the genesis of that number. The only thing I've found in common is that none of them are common, and none of them are based on any form of measurement or scientific data. So that's what we wanted to obtain. Our project was basically pretty simple. We need to understand the inhalation risk during application underground. And then from that, we needed to determine evidence-based exclusion zones, which most importantly protected the health of the coal mine workers. But also, point 3, very important, did not impose unnecessary restrictions to the detriment of other safe mining practices. Now you think to yourself, why does a regulator want to lower an existing safety standard? Well, from our point of view, and from the information we had and the suspicions we had this massive zone where it was actually quite safe to put people. We couldn't allow anything else to happen, but potentially we could be doing other safety critical tasks in there. You know, we could have people in the tailgate, installing pumpable cribs, doing maintenance on shields, or even potentially, if we had a really smashed up face, we could be attacking cavities, fractured ground from 2 injection points, which under the current regime is not prohibited. That would allow us to regain control and get moving quicker. But in order to do this and reduce the safety standard, we need to be really confident about the evidence we obtain. So firstly, we need to be confident when we did our measurement, we knew exactly what was in the chemicals that we were dealing with. We also need to be really confident that the measuring techniques we used were capable and sensitive enough to capture everything. And of course, this wasn't going to cut the mustard if we just did this in a laboratory setting. We needed to take our methodologies, our measurement, and go underground when they were being used in anger and do our assessment there. And finally, the other thing, and potentially one of the reasons for these massive exclusion zones, was the concept of an uncontrolled release, whether we had a major spill or whether potentially, under pressure, one of our lines had developed a pinhole leak and we potentially atomised isocyanate into the atmosphere. And that was probably one of the things which I thought justified the 350, one of the concepts around the original notions for that. So I'll just really go quickly through this project. Firstly, understanding what was in the mix. Again, as Geoff said, we used all the suppliers licensed in New South Wales and operating in Queensland, and they provided all of their raw products for us to test. So, and no matter what product you use, Minova, Wilson's, the MDI, which is the isocyanate, part B, is methylene diphenyl diisocyanate, 99%. That's what the SDS says. Why MDI? Because in terms of isocyanates, it has a high molecular weight, a relatively low vapor pressure, and it's quite easy to handle, making it safer. So SDS will tell you 99%. So we wanted to actually test if that's what you were getting, and there were no other nasties in there. The other point, we also wanted to understand, did the curing mixing process create any additional hazardous substances that we weren't accounting for? So to do that, you can see these photos. We actually got IBCs. We filled with a portion of each of the manufacturer suppliers' isocyanate, and we allowed it to reach vapor saturation overnight, and we sealed the containers and turned on our monitors. Now, we weren't trying to replicate personal exposure or make some sort of assessment of risk. We just wanted to identify what is in these substances in the air, in that headspace. And we did exactly the same with each of the suppliers and got them to pump, mix, and allow their foams to cure and expand, and our monitors sitting in that headspace measuring what came off. Now, while we did this, I mentioned before, we wanted to understand the most reliable methods for measurement. So we took the opportunity while doing these tests to test 3 commercially available methods. Firstly, the OSHA filter method, which is probably the one that's used most commonly for doing isocyanate assessment across all industries, and particularly the only one I've known to be used in coal mines. We tested that. We tested a US method, which is a slight variation, and we tested the asset sampler, which was relatively new, and it had claims of being able to be to do a broader range of isocyanates and also to be much more sensitive. Now, I'm missing a slide there, but that's okay. We've had problems with this, but what I can tell you, okay, what we should have found, what we really should have found, and we expected to find in this headspaces was MDI. 99% MDI was the claim of the SDS, and we should have found a bunch of MDI monomers in there, and that would have been simple. But what did we actually found? We found phenyl isocyanate, methyl isocyanate, we found isophorone isocyanate, we found all these contaminant isocyanate species that shouldn't have been there. And what's really important when measuring isocyanates is there's attached to the molecule is an NCO ring, and that's the one that elicits the health effects. And it doesn't matter which isocyanate, they all have them. It's the combination or the addition of those is what we need to compare against the exposure standard. So if we were only targeting MDI using the filter method, we wouldn't have picked up any of these other species, and we would have severely underestimated the exposure risk. So moving forward, now we knew what we had to look for, and sorry, I jump ahead without that slide. There was only one of those methods that had the capability and the sensitivity to detect all these species, and that was that asset sampler there on the right. It was highly sensitive. It detected down to a very low concentration, and it had the broadest range by far. And we did over 130 tests, I should say that, and the findings were very, very statistically significant. So now we had our method, and we knew what we were looking for. We knew how to sample it. We took the testing underground, and we did static sampling, so fixed position, and personal sampling on operators. And I'll just run through a couple of examples, but we measured during sprayed lining, we measured during PUR injection, we measured during USR injection, and seal and spraying seals and the like. And here's one example. This is Cabra Downs. This was on a shoulder of a tailgate. It was really fractured ground using GeoFlex, it's a reused silicate product, and it was taking full volume in those holes. We had a sampler on the nozzle operator, and we had this row of samples 10 metres from the injection point. and 50 metres. And you can see those numbers there, right? What I need to tell you is that the exposure standard for total NCO or isocyanate is 0.02. And you can see that where we have a less than sign, that meant we couldn't detect, so below limits of detection. And where we don't is the concentration value we recorded were all much, much lower than the exposure standard. In fact, factors lower. So we thought, well, that was our first job. Then we repeated at various mines. Here's another one. This is Broadmeadow. This was standard PUR. This was pre-consolidation work. And again, this time we got a little bit cheekier and we couldn't detect anything at 10 metres, so we stepped into 5 metres. And again, no detections. Very importantly, on the operators as well, no inhalation or no atmospheric concentrations detected. And so on, we went and we did full spraying, worst case scenarios. We got them to spray rib to floor to roof for an hour in an area and set up our monitors, and again, similar results. So we were fairly confident in the evidence we were accumulating. Now we needed to look at the uncontrolled emissions. Now, there wasn't a mine in Queensland that was going to allow us to have a major spill underground with raw isocyanate, so we had to look at another suitable solution. We went back to the suppliers, we got them to sacrifice a few IBCs, and we modified them, and we actually contained raw isocyanate in the bottom of those. We got a fan, we blew 0.5 metres per second over the top of that, and we had our monitors stationed directly opposite. Same findings. Very, very, very low levels of isocyanate. The ones we actually picked up were the other contaminant species, not the MDI, but very, very low levels. A worst case scenario, when you think about it, if you had a spill underground, most of that product's going to run off to the side or be absorbed into the coal, so you're not going to have give it the opportunity to get into the airstream. So that was a good test, gave us a lot of information. We repeated that with all products. And finally this notion of, could we atomise this product under operating conditions in the underground environment? Now tell me that you can atomise honey if you try hard enough, but in this scenario, no one was going to allow it to test this, so we had to get an independent engineering study. And they looked at all modes of operation and tried their best to theoretically atomise this based on hose design, which is required for the use of these products, pump design, viscosities, hole size. It was significant to a degree, impossible to atomise underground in current scenarios. So now we sort of had all this information, which puts us in a position now to have a evidence-based discussion with the stakeholders about potentially reducing these zones. So just in summary, 60%, so we're now up over 60 samples collected underground. About 60% or a touch over have not detected any isocyanate. 90% have either not detected or below 10% of the exposure standard, which in hygiene terms is very, very low risk. We've also shown that, and none of the measured values have even approached half the OEL, which again is an action level in hygiene terms, and we got nowhere near that. We've also shown we're not going to get any significant risk during a spill, or we can't atomise the product. What we do know, however, is that the primary route of exposure for these particular type of isocyanates is skin contact. So we're not going to budge on that, and our monitoring and controls are going to be all about skin contact, but we are in a position now to start having a meaningful discussion about bringing those zones in so that we can effectively empower mines to improve safety outcomes and also assist productivity. So that's a win-win for everyone. And I'm pleased to say that everyone's been on the journey and supported it with the evidence. And that's what it's all about, getting the objective evidence to enable you to have those discussions and take out the emotion. So with that, yep, that's about it. Thanks very much.
Thanks, mate.